Okay. So, homework 12 is right here. I'll give you homework 13. It's here in my hand. And there is a homework 14 on our schedule, but as I was mentioning as we were getting started, I will probably reduce that, try and work in some of the problems to an in-class exercise, and then maybe have you submit a couple others. And so I'll let you know next time what we'll be doing for homework 14. This homework 13 that I've given you is all about water surface profiles, and the nice advantage here of getting it as a handout is that I've told you which method to use, and that wasn't necessarily clear, I think, in some of the authors in the problems themselves. And so I tell you for problem 2, use numerical integration method. 23, use step-by-step, which is what we are going to be covering today. And then 36, standard step method. We're going to talk about the standard step method in class on Thursday. And then this handout, there's one more problem besides those 3 book problems that's also standard step method. So by Thursday, you'll have all the information. You'll have a couple of 3 spreadsheet templates that you can use to solve the problems. So I think you'll be able to sail through it without a care in the world. Yeah, you will have Excel access on the final exam. It is. It's cumulative with an emphasis on material covered since the 2nd midterm exam. Yeah. So we'll talk about the final exam in a future class, including the equation sheet situation. I think that most likely I'll be providing an equation sheet for you, and I'll give that to you in advance so that you can familiarize yourself with what the equations look like and where they are on the page and so forth. All right, so as I mentioned, today we're going to be covering the direct step method, and we may actually end a little bit early with this. I've just got one example illustration to walk you through. The intent of the lecture is for us together build a template that you can use for the direct step method as you apply that into the homework assignment. So any questions before we move forward? All right, well, I'll dim the lights here so you can see the picture of a river. And have I ever told you that when I was working on my master's degree, one of my 10 classes that I took for my master's degree was basically we would go to a room, the professor was checked out. You know, he was basically retired already but still drawing a paycheck. So he put us in a room and put these videos on. It was just videos of running water, like soothing, gurgling sounds and different rivers and mountain streams and waterfalls. I mean, ostensibly it was like an EPA training video about water quality, but the information per hour was so low. It was just these beautiful nature videos that we watched, and that was 3 credits of my master's degree, was watching those videos. And so anytime I put up a really nice picture of like some mountain stream, I always hearken back to my nice class in water quality, CE 550. I miss it. I labored to stay awake because it was so relaxing. So this direct step method is sometimes called the step-by-step method, and it gets that name because what we're going to do is break the profile up into pieces. And it's a direct extension of the numerical integration method. Remember that in class last time we worked an example where we found the length of the profile using one section, and then we broke it up into pieces, and we were looking at, if I remember correctly, maybe it was an M3 profile where we looked, you know, what is the length of the profile if we take this jump in a single step, or what if instead we are finding what is L if we go from 1 to 2, and then go from 1 to 2 for the second half of it. And the 2 values in that illustration were relatively close. I think they were within a meter for the length of the profile, and that's not too bad. But there are times where you have a water surface profile that's changing more abruptly, or you have a really long profile that exceeds sort of the upper limit that you can apply in a single step. And so the direct step method is a way of taking multiple steps and showing it all on a single page. In the direct step method, sometimes since you've got calculators in a vertical sense that you're iterating to get the solution, then you can't really preserve and display what the length of each of the different segments are. I'll show you what I mean by that as we look at the template. But remember that in the direct step method and all the other water surface profile computational methods, what we're looking at is non-uniform flow and gradually varying non-uniform flow. We're trying to find out when we have two sections of water where there's a differing depth between them, what does that water surface look like? And I'll remind you that it's important to memorize different profile types, like how to classify M1, M2, M3, S1, S2, S3. We'll have a quiz next time, and I'll give you a question where I ask you to identify what kind of a water surface profile we have. So you can review the notes on that or go back through the lecture, read the book, but it's not hard once you sort of keep in mind how to diagnose it based on the critical depth and the normal depth. Okay, so in the direct step method, this is the same diagram we've seen before where we have water flowing downhill over a slope S0. The water surface may not be parallel to the channel slope. In this case, it's not immediately obvious whether it is or it isn't. But the idea of the step-by-step method is to consider the energy at location 1 and location 2. And you can see here that the delta Z that we're referring to at location 1, S0 times dl, that's simply the elevation difference between the upstream section and the downstream section. And so we're saying that the energy here at the top of the total energy line, or the energy grade line, as we called it back in fluid mechanics, all of the energy can be accounted for by the depth, the velocity head, and then also the losses at location 2. And so S sub F times dl. S sub F is the slope of the energy grade line, and S sub F times dl is this section that's indicating how much energy was lost. And in uniform flow, S sub F dl is equal to S0 dl. But in non-uniform flow, those two aren't equal at all. And so we can rearrange that equation to say what is the difference in energy between location 1 and location 2. And you can see the result of that rearranging. And we can calculate the average slope of the energy grade line. And that's sort of what we were doing in the numerical integration method, is we are looking at between the two sections what's going on at the middle. And so S bar, F, is meaning the energy grade line between 1 and 2. It's the average of the two. And so the length of the curve is going to be the change in energy loss divided by the difference in the slopes. And that's the approach that we're going to be applying as we work through this illustration. When we have subcritical flow, we'll start at a downstream location and work upstream, and vice versa if it's supercritical flow. If it's supercritical flow, meaning that the Froude number is above 1, or you necessarily don't have to calculate the Froude number to tell if you've got supercritical flow. You can also tell if you've got supercritical flow if the normal depth is less than the critical depth. And that's another way of diagnosing whether you've got an S water profile versus an M water profile. And we'll divide a reach into several segments, but we don't want the change in water depth to be any more than 0.5 meters per step. I'll show you how to apply that limitation. And of course, the more steps that you break your water curve into, the more accurate it's going to be. And the reason for that, of course, is that what we're trying to do is we're trying to approximate a curve as a series of lines. And so here we've got a curve. That's what it actually looks like. And if we just break it up into 2 steps, then essentially we're saying that this is what the curve looks like, is that it's linear. And so the more pieces we can break that up into, the more accurately we can model a curve as a series of lines. Okay, so let's apply it to a channel that here is described as being rectangular, has a 7-meter width. Okay, we've got an n value of 0.02, and it's carrying a flow. Q is 15 cubic meters per second. And there's a broad-crusted weir downstream, and you can see that that broad-crusted weir is causing a backwater condition. There's some choking. And the choking, of course, occurs here until there's enough energy to get the flow over the broad-crusted weir at the critical depth. And that's why the water pools, is that there wasn't enough specific energy initially to get the water over that weir. And we know that at the upstream end of the weir, the depth is 3.8. So that's talking about right here, the depth is 3.8. We're going to break that up into segments and calculate the depth at each of the segments. But before we do that, we have to get some preliminaries out of the way. We need to calculate the critical depth and the normal depth. And like I've mentioned before, when you're doing non-uniform flow problems, you're always in good shape calculating the critical depth and the normal depth. If you're a deer in the headlights and don't know how to go on the problem, then you'll always be making valuable use of your time by calculating the critical depth and the normal depth. And since this is a rectangular channel, we can calculate the critical depth according to this formula: flow per unit width squared divided by g, all that to the 1/3 power. And so we've got 15 cubic meters per second divided by the 7-meter width. That'll give us the flow per unit width. Square that, divided by 9.81 meters per second squared. All that's to the 1/3 power. So our critical depth is 0.7764 meters. And normal depth, we calculate with Manning's equation, of course. Q equals 1 over n, a to the 5/3 power, wetted perimeter to the 2/3 power, slope to the 1/2. And so we have 15 cubic meters per second, 1 divided by 0.02. Seven times the normal depth is our cross-sectional area, because 7 is the width, and Manning's equation, the y that you're going to solve for in Manning's equation, is always the normal depth. And then the wetted perimeter will be 2 times the normal depth plus 7. All right, and we'll take the area to the 5/3 power, the wetted perimeter to the 2/3 power, and then the slope here, the channel slope is defined as 0.0015, so 0.15%, 1/2 power. All right, and put that into your solver, and it's becoming second nature to solve Manning's equation, hopefully in your calculator. You'll get that the normal depth is 1.195 meters. So what that means is that if you go far enough upstream where the influence of that broad-crested weir is no longer seen, if you go far enough upstream, you'll get back to uniform flow. And the depth of the uniform flow is where it's 1.195 meters here. And then we measured the depth right upstream of this broad-crested weir. We measured the depth was 3.8 meters. And so what we're wondering is what does that curve look like? How far do we have to go upstream of this broad-crested weir before it's back to its normal depth? Now, can you think of a practical application where calculating the length of a backwater curve could be important? Maybe here in the state of West Virginia? Okay, with a dam? Yeah, when you dam a river, and create a reservoir, then it's going to be important to know how far upstream you got to go before that pooling doesn't exist anymore. And even on a smaller level, when someone puts in a culvert, like on a small creek, they're not supposed to put in culverts that will choke the flow at all. It's supposed to be able to pass the 100-year storm through a culvert without any backwater forming. And so, when there are obstructions in the way, you have to have some sort of an analytical method that will tell you how far upstream the water is going to be disturbed by an obstruction. There could be homes that if the water level rises too much, it's going to wreak havoc with the home. So the process that we're going to go through is, let's see, we found the critical depth and we found the normal depth. How do we diagnose the water surface profile type? We've got YC and YN, and then we know the actual depth is, the given Y is 3.8 meters, immediately upstream of the of that broad-crested weir. And so what kind of a profile do we have when Y is 3.8, and that's greater than Y sub n, which is 1.195 meters, and that's greater than Y sub c, which is 0.7764 meters. M1. Yeah. So remember that the two lines, the critical depth and the normal depth, divide the channel into zones. And so in our calculations, we said that we have this critical depth, Y sub c was the 0.77, right? 0.77 meters. The normal depth is 1.195 meters. And so that makes this zone 1, that zone 2, and this zone 3. The fact that the normal depth is bigger than the critical depth, that makes it M. Because anytime normal is bigger than Y sub c, it's M. If normal depth is less than Y sub c, that makes it S. And if normal depth and critical depth are equal, then that's a critical slope, a C. Okay, so it's M because Yn is greater than Yc. And then the given depth of 3.8 meters means that the actual water depth, here's the water surface depicted with a triangle and the little ripples there, puts it into zone 1. So that's how it's an M1 profile. So how many segments should we use? If the guideline is that we don't want to have any more of our elevation changes more than a ½ meter. Let me raise the screen a little bit here. This is one of the times that I'm glad to have a whiteboard immediately behind the projector screen because it allows me to do this. We've got 3.8 meters of depth. And up here is where we get to the normal depth of 1.195 meters. 1.195 meters. And we don't want the elevation difference in any one of these steps to be more than ½ meter. And so basically our delta Z that we're going to do is we're going to go from 3.8 meters to 1.195 meters. And we don't want any more of the steps to be larger than 0.5 meters in elevation. That means that we should use 5.21 segments. In other words, we'll use 6. And each of the 6 that we're going to use is going to have an elevation difference of 0.43417. And I just got that by this number is the elevation difference, the total elevation difference divided by 6. And so here is 3.8. This one, let me write it underneath. The elevation is 1.195. This one will be 1.629, 2.063, 2.497, 2.932, 3.366, and then 3.8. And the question that is going to be solved by this spreadsheet in steps is how far apart are each of these segments? And then we'll find the total length by summing up each of the segment lengths. So any questions on what the strategy of this approach is going to be? All right. Yeah, this is 3.8 meters minus 1.195 meters divided by the 6 segments. And so I know that I don't want the change in elevation of the water to be more than half a meter in any single step. So I just, by doing this, found I should have at least 5.21 steps, and I'll round that up to the nearest integer, round that up, because I don't want them to be larger. And so this tells me the elevation difference. That's, using this number is how I calculated each of these depths. So, I mean, of course, between 3.8 and 1.195, there's going to be some depth where it's 1.629. And I just happened to draw this arrow to symbolize that there is some point along this water surface where that's the depth. I mean, there's nothing magical about this number. I could say, well, let's calculate 1.6, 2, 2.5, 3, and then I just find out what is the length between the locations where the depth upstream and the depth downstream is specified. But here? Yeah, I could make it smaller, and I'll get better results the smaller I make that, the more steps you do. Okay, so let's take a few minutes. I'm going to be quiet while you set this spreadsheet up. Basically, just translate the what I've given you on paper into an Excel spreadsheet, and then I'll walk you through the procedure of how we calculate the overall length of the backwater curve. The DLs. Yeah. We're going to total the DLs later. All right. So let's just refresh our memory what we're doing. We know what we're going to use as these depths, and we're going to find the individual lengths between each depth by calculating this formula. And what we'll have to do is at each upstream and downstream segment, we're going to have to know what is the slope of the energy grade line, and we're going to accomplish that by using Manning's equation to calculate, you know, at this particular location, what's the slope of the energy grade line using Manning's equation, and then we will take the average of the two. Is it doing a... Yeah? All right. So I've put in the depths that we're going to use, and you'll notice that there's spacing in between, and the reason is that some of the calculations we're going to do for the midpoint, and some of the calculations we're going to do at that section of interest. And so, for example, here where the depth is 3.8, I want to know what is the cross-sectional area, and the cross-sectional area is simply going to be the depth times the channel width, because, you know, it's a rectangular channel, and so that's how we calculate the cross-sectional area, and I can drag that down since I anchored the reference to the channel width, and then I'm just going to delete all the locations here where it had a 0 because there, you know, it was the segment between. Feel free to interject with a question if you've got one. Okay, the velocity is going to be, again, for each of the segments, not for the midpoints yet. We'll get to the midpoints in a little bit. But for the velocity, it's simply going to be the flow rate, Q, and again, anchoring that, you can press F4 to anchor it, divided by the area, and then drag that through, and delete the locations where it says divided by 0. We don't need to see that. And you'll notice that I think just because this is a spreadsheet that I've previously formatted, it's only displaying 3 digits of precision here after the decimal. And you know, there's no value really of having a spreadsheet full of extra digits that don't really tell you anything more. So it's just a good practice to sort of keep it tidy and not show too much. Now for the E, that formula is going to be the depth plus the velocity head. So what we're talking about is the specific energy at that location. So equals the depth plus V squared. So I'll click here on my V cell, square that, divided by 2G. Divided by 2, divided by 9.81. So that's divided by 2G. So now I've got the specific energy at that location. The formula for it is the depth plus V squared divided by 2G. Another way I could have done it was equals the depth plus V squared divided by 2 times 9.81. All right, drag that through. Yeah, all the way to the bottom. Well, we're just going to delete where it's listing for the midpoints. Yeah. Okay, now finally we're going to, once we've done that, the delta E is talking about how much energy loss is there between 2 segments. And so this delta E column is going to say between the location where the depth is 3.8 meters and the upstream location from that where the depth is 3.366, what's the energy loss? Now the energy loss is going to be dependent on the change in depth and the change in velocity head. So all I'll have to do is equals the upstream section minus the downstream section. So I'm going to get a negative number for that. So the delta E is negative in the direction of flow, meaning that we're losing energy as we go from segment to segment. And let's see, can I drag that and have it be meaningful? Yeah, I just have to delete every other cell. Another way of, besides dragging, you can do Control-C and then just paste in the location with Control-V, and it does a relative calculation based on the position. All right. Oh, that's good. Does the pattern, alternating pattern. All right. So do we need to take a pause here? Any questions? Anyone not up to speed yet? We're good? All right. So that is the energy loss between sections. Now, for the hydraulic radius, we're again doing the calculation for the section itself. And the hydraulic radius is going to be the channel width of 7 meters. Let's see, hydraulic radius, area divided by wetted perimeter. Right. So the area here, start with the area, divided by the wetted perimeter, which is 7 meters plus 2 times the depth. So the units of meters, because we've got cross-sectional area meters squared divided by the wetted perimeter, which is meters. So that leaves us with the hydraulic radius in terms of meters. So the area divided by the channel width, and I've anchored the reference up here to the channel width, times 2 times the depth, plus 2 times the depth. Okay. So hydraulic radius, we'll try Kevin's trick, select both cells, Control V. Oh, that's great. Just drag it? Right, okay, we'll do that. I want to try it out. All right. That's nice. Okay. Now the slope of the energy grade line, we're going to be using Manning's equation. So we have to type Manning's equation in here. It'll be the n value, anchor that reference, times the flow rate, also fixed, divided by the area, divided by the hydraulic radius. Now, I've got my cells centered, so you can see how the equation is bleeding over into the cell that I actually want to click into. So I'm going to have to actually type F14 like a barbarian to the 2/3 power. I remember the bad old days when like computers didn't have a mouse and you literally had to type every cell reference. It was a nightmare. You guys don't know how good you have it. Squared. All right. Yeah. I guess what I could have done is just taken my cell alignment to the left, and then as I was typing in the equation, it wouldn't have bled over, but who can be bothered? I wish there was some way to make these formulas appear larger. Well, I can zoom in on this, but it doesn't change the size of the formula displayed in this bar. Yeah. All right, so then we drag that through. All right, and we've got the slope of the energy grade line at the location. So, of course, the average slope of the energy grade line is going to be the average of the upstream and the downstream sections. So you can do AVG, no, average of these two. Or you could add them and divide by 2. So I've got the average slope of the energy grade line, and so that is considering, you know, between the sections, what is the slope of the energy grade line there. And that's what we're going to use in this next column, S naught minus the average. So the S naught is fixed. The channel slope is 0.0015 meters minus the average slope of the energy grade line. That's right, yep. I anchored that reference up here. Yeah. It's this one minus that one.
Oh, okay, so this one.
Yeah. Yep. You can just drag that down. Everybody doing good? Any questions? Getting it okay? Well, this needs to be that minus. Oh, you're still working on it? Okay. 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 Getting ready for the big finish here, the DL. Yes. Okay. So you need to calculate the average for all of these. So first of all, drag that down. Okay. Let's see. Oh, it's just that and that, those two. Yeah. So SF, do you have the SF correctly? Let's see, V, E, delta E. Okay, so the formula here, click in here. It should be N minus Q. Okay, anchor Q, C3, anchor that. Divided by area. Okay, divided by, not depth, area. Yeah, good. Divided by hydraulic radius, good. Yep, fine. Finish. Okay, good. Now drag through. And then this will be average of these two. Okay, so finally the DL formula here. We'll calculate the DLs using this equation. So it will be delta E, this delta E from over here, divided by the difference of S naught minus the average energy grade line slope. So divided by that. And that tells us how far apart, and the minus means upstream. It means to go from where it's 3.8 meters to 3.366 meters, you have to go 299 meters upstream. So this is a really long, gradual profile. And the reason why it's so profile is that this is such a shallow slope. You know, 0.1% is a very flat river. And so it's going to take forever. Well, not literally forever, but it's going to take 2.4 kilometers upstream before you finally get back to the normal depth. So the interesting thing about this is, remember that I said that these points were, sort of picked arbitrarily, the depths that we were interested in, and you could play around with, we could say, well, what if we want to go to 3.4, and it'll automatically update all of the depths, all the calculations if you pick different depths here. So let me circulate around and answer any questions that you have. The announcements here, just to finish things off. Oh, the design project is due on Thursday. I guess we didn't talk about that at the beginning of class. All I need from you is the printed report, and remember the assignment description has the most detailed description of what should be in the final report. I'll contact you if I need to see your WaterCAD files or if I need to see a spreadsheet, but since I've already been through much of what you're submitting, in most cases I don't expect to need to see the digital files.
What if we do a little bit more WaterCAD? Print it out then? Or you'll just...
Okay, so you bring up a good point. In your submission, what I'd like you to submit is your finished project. What's the final design, including an updated annotated map, updated spreadsheet, and then if you've made substantial revisions to your water design or to your spreadsheet since it was initially submitted, then include the original draft submissions as an appendix. So, like if I pointed out some serious errors in the draft stage, show me the finished stage, and then in the back include the draft, just so you can illustrate the updates and edits that you've made. Other questions about the project on Thursday? All right, that's it for today. I'll see you on Thursday. We'll get into the standard step method. Yeah, bring your computers on Thursday also.